Okay, we're going to continue our discussion of condensations and alpha substitutions of carbonyl compounds. And where we left off was we're going to look at the malonic ester synthesis. Okay, malonic acid is propane dioic acid. And the hydrogens between the two carbonyls are unusually acidic. They're about pK 13. And so using sodium ethoxide, we want to use the same alkoxide group as on the ester. Otherwise, we'll get scrambling. Okay, so this removes an alpha hydrogen, and then we can alkylate that to form an alkylated malonic ester. Okay, something else that we can do is that we can hydrolyze both of these esters. Okay, we talked about hydrolysis in the previous chapter where we split an ester into an alcohol and a carboxylic acid. But what's unique about malonic acid and substituted malonic acids is that upon heating, one of the carboxylic acid groups gets lost as carbon dioxide. And so our final product is a substituted acetic acid. Okay, this is the mechanism of decarboxylation. Okay, if that means loss of carbon dioxide. This goes through a cyclic mechanism. Okay, oxygen picks up a hydrogen from the other carboxylic acid. We form a CO double bond. This carbon-carbon bond breaks. Okay, so we split out carbon dioxide, and then initially we get the tautomer, or the enolate, of the carboxylic acid, which then rearranges to the substituted acetic acid. All right, so here we have some examples of malonic synthesis. This area shaded in blue, the other ester group, serves as a temporary ester group. Okay, so we can very rapidly deprotonate and do a SN substitution, SN2 substitution at this position. We add the R group, and then upon hydrolysis and heating, we lose carbon dioxide. Okay, so the question is show how the malonic ester synthesis can be used to prepare 2-benzyl butanoic acid. Okay, so we start out with our malonic ester, and we do a benzyl substitution on the one of the middle hydrogens. So we introduce our benzyl group here. Okay, and then we can actually do this again. We can deprotonate a second time and do another SN2 substitution. So we have the benzyl and the ethyl. And then upon hydrolysis and heating, we remove one of the carboxylic acid groups. And in this example, we now have a disubstituted acetic acid. The acetoacetic acid ester synthesis is very similar to the malonic ester synthesis. except that instead of two esters, we have an ester and a ketone. Even though we have two sets of alpha hydrogens, it's the hydrogens that are between the two carbonyls that are much more acidic. Okay, so we remove one of those alpha hydrogens, we do the alkylation, and when we hydrolyze and heat, again, we lose carbon dioxide from the carboxylic acid. And so our product is a substituted acetone. Okay, so here's an example. We remove this hydrogen using ethoxide. That produces ethanol. Okay, this undergoes an SN2 substitution with our alkyl halide. Okay, so we alkylate. And then when we hydrolyze, we convert the ester into the ethanol and the carboxylic acid. And then upon heating, this loses carbon dioxide. And the mechanism for decarboxylation is very similar to that of malonic acid decarboxylation. Okay, so here, how would you make 3-propyl hex 5-ene 2-one? Okay, so we could start out with the acetoacetic ester. Okay, we substitute a propyl group here for one of the hydrogens. We do this a second time. We remove this other hydrogen, and then we replace it with this allyl group. And then upon hydrolysis, we get the beta keto acid, and upon heating, we lose carbon dioxide. We lose the carboxylic acid as carbon dioxide. Right, next we're going to look at the Michael addition, or conjugate addition. And if we have an alpha-beta unsaturated carbonyl, these have unusually electrophilic double bonds. The beta carbon is electrophilic because it shares the partial positive charge of the carbonyl carbon through resonance. If you look at the resonance structures, okay, we have an electrophilic carbon here with the carbonyl, and then we also have an electrophilic carbon here at the beta position. Okay, so there are two possible addition sites. There's what we call 1,2 at the carbonyl, or 1,4 where we add to the alkene. Okay, these are acceptors and donors that promote the Michael or 1,4 addition. Okay, and what these are softer nucleophiles. That is, the negative charge is more spread out. Okay, if you have a hard nucleophile, okay, one in which the negative charge is very concentrated. An example would be like an alkyl lithium. That will favor the carbonyl carbon, or a Grignard will favor the carbonyl carbon. Okay, but these softer nucleophiles where the charge is more spread out, these are going to favor the beta carbon. Okay, so these are examples of softer nucleophiles. These include the Gilman reagent, dialkyl lithium cuprate, enamines, beta diketone enolates, beta ketoesters, beta ketonitriles, and alpha nitroketones. Okay, and then these are acceptors. The Michael donors will attack the beta position of these conjugated compounds: aldehydes, ketones, esters, amides, nitriles, and nitroethylene. Okay, so the malonic ester enolate is a soft nucleophile. The negative charge is spread out through resonance, so this attacks the carbon of methylphenyl ketone. That pushes electrons up onto the oxygen. Oxygen pushes down, and then this carbon then picks up a hydrogen from our ethanol. Okay, so we get carbon protonation rather than oxygen protonation. Okay, so this occurs very readily. The 1,4 addition product occurs in about 90% yield. Okay, so show how the following diketone might be synthesized using a Michael addition. Okay, so here's our carbonyl. Okay, so we count over alpha, beta, and then we would disconnect here. Okay, so disconnecting, we would have a double bond at this position, and in order to favor attack on the beta carbon, we would want okay, imagine this is disconnected. We would want we'd want an ester group here. Okay, so we broke the bond after the beta carbon, so this becomes our Michael acceptor. And then here we have our Michael donor. And again, we'd likely have another ester group that we would hydrolyze and decarboxylate. Okay, here, this is the Robinson annulation, and this was named after a British chemist named Sir Robert Robinson, and this is a combination of a Michael addition and an aldol cyclization dehydration. Okay, so 2-methyl cyclohexanone forms this new cyclohexanone with methylvinyl ketone. Okay, so the first step is that hydroxide removes this hydrogen. The more substituted alkene is favored. This is an equilibrium. The enolate anion then attacks the beta position here. Okay, that pushes electrons up onto the oxygen. The alpha carbon gets protonated when oxygen pushes down. Okay, so we've got this beta diketone. Okay, so we have alpha hydrogens here. We've got alpha hydrogens on the methyl. We have alpha hydrogens here. But remember, 5 and 6 membered rings are favored. So if we form the cyclic compound here, we would just have a 4-membered ring. So that's not thermodynamically favored. Okay, so we're going to remove a hydrogen from this position. Okay, that will attack this carbonyl carbon, and oxygen will become protonated. So this is our aldol product. And then this can easily undergo dehydration. Normally, hydroxide's not a good leaving group, but this is thermodynamically favored because we form a alpha-beta unsaturated ketone.